Bienvenidos al ciclo de conferencias Universidades por la Ciencia, organizado por Fundación UNAM, Colegio Nacional y el conjunto de universidades y centros de investigación del Consorcio Universidades por la Ciencia en México, Estados Unidos, Reino Unido, Brasil, Argentina, Chile. Les agradecemos mucho el interés en estas conferencias y el día de hoy tenemos una muy especial a cargo de la profesora Wendy Freedman de la Universidad de Chicago. La doctora Freedman es profesora de astronomía y astrofísica en la Universidad de Chicago y una especialista en el estudio del universo. Ha sido directora de los observatorios en Estados Unidos, en Pasadena, también en las Islas Canarias. Y el día de hoy la conferencia es sobre la expansión del universo a través de las observaciones en los telescopios de Hubble y de Webb. Le agradecemos mucho que nos acepte la invitación y en el panel nos acompaña el presidente de Fundación UNAM, el licenciado Dionisio, la directora ejecutiva de Fundación, Araxi Rodríguez, la presidenta del Consorcio de Universidades por la Ciencia, Araxi, Urrutia, y el Centro de Estudios Mexicanos de la Universidad de Chicago, nuestra secretaria ejecutiva, Wendy y Alberto nos acompañan desde Chicago. Welcome to the Universities for Science Seminar Series organized by Fundación UNAM, Colegio Nacional, and the universities and research centers of the Consortium in Mexico, the US, UK, Brazil, Argentina, and Chile. Today we have a very special conference by Dr. Wendy Freedman. She is the professor of astronomy and astrophysics in the University of Chicago. And today she will present talk about the expansion of the universe and through the observations of the telescopes Hubble and Webb. Thanks very much, Dr. Freedman, for accepting this invitation. And Dr. Freedman has a very extraordinary research trajectory, and she has been the director of the observatories in Pasadena, in California, and also in Canaries, in the Canaries Islands. And we are looking forward for this conference and also for the collaboration we are establishing with the University of Chicago. Thanks very much. And I will introduce our president of the UNAM Foundation, Dionisio. Thanks. And at the start, we will go back and forth in English and Spanish, and then we will have the conference and we will welcome comments and questions. Thanks very much.
Pues muchas gracias de nuevo a todo nuestro auditorio. Agradecemos la presencia de nuestra conferencista de hoy, de Wendy Freedman, y queremos subrayar un hecho muy especial. Es la primera vez que para hacer estas presentaciones estamos juntos, Araxi, que es la presidenta de nuestro consorcio, Jaime Urrutia, que ha sido un impulsor de este proyecto y que lo ha hecho desde su fachada en la universidad, desde nuestro consejo en fundación y desde la plataforma del Colegio Nacional. Tuvimos un poquito de demora porque ustedes se imaginarán que para conectarse en el espacio con el Hubble y el Webb, pues sí teníamos que transitar por un poquito de distancia. Pero ya estamos comunicados, estamos muy agradecidos y muy contentos. Además, este espacio de hoy pues, es verdaderamente innovador. Nos vamos a internar en lo que hasta ahora es el corazón del espacio, con los descubrimientos y con las posibilidades que nos ofrecen estos dos telescopios formidables. Y además, la gran virtud de una presentación como esta es que nos permite compartir con nuestro auditorio y que nuestro auditorio pueda formular preguntas e inquietudes a nuestro conferencista. Sí sentimos que cada una de estas pláticas de investigaciones en curso ofrece un horizonte formidable y que muchos de quienes ahora están escuchando esta presentación Seguramente habrán de interesarse en algunos de los temas que hoy se presentan. Quisiéramos que así como hoy está Wendy Freedman dándonos una presentación, el día de mañana sean nuestros escuchas actuales quienes puedan acompañarla para hacer presentaciones similares. Muchísimas gracias, es un orgullo tenerlos aquí y es un orgullo esta presentación innovadora, formidable, que tendremos oportunidad de escuchar el día de hoy. Muchas gracias a todos y bienvenidos.
Thanks very much. And now Erika from UNAM Chicago will introduce Dr. Wendy Freedman.
Thank you very much, Dr. Urrutia, America Erdely, Academic Coordinator at UNAM branch in Chicago. And it's my great, great pleasure to welcome our outstanding guest speaker today. She is Wendy Freedman. We already heard a little bit about her from Dr. Urrutia. I'm just going to add that she's affiliated to the Kavli Institute for Cosmological Physics at the University of Chicago, one of the most prestigious universities in the Midwest of the United States and in the whole country altogether. So as has been said, she's a university professor in astronomy and astrophysics. Her research is in observational cosmology, measures of the expansion rate of the universe using the Hubble Space Telescope, Spitzer Space Telescope, and the ground-based Magellan Telescope. Her current projects involve measurements of the Hubble constant, the current expansion rate, as well as the past expansion rate, providing constraints on the acceleration of the universe and dark energy. Her other fields of interest is the stellar populations of galaxies, the evolution of galaxies, and the initial mass function. Thank you very much, Dr. Freedman, for being with us today, for your generosity in sharing your knowledge with us. So please go ahead with your talk.
Thank you very much for the invitation. And I will say at the outset, I apologize. I'm having some technical difficulties this morning. The entire connection in my local area has gone down. So I'm giving my talk by cell phone, and I have never done that before. So I believe I'm going to go in and out. It has already happened a couple times, but I will come back and we'll just proceed. So let me just ask, are you hearing me? Can you hear me?
Yes, yes.
Oh, good. So I see a message that you've started screen sharing, but it hasn't come up for me. I'm going to stop my video in the hopes that that will also help the connection, but I don't yet see the screen. It hasn't come up for me. In any case, I'll start and hope that the slides will, here we go, excellent, will come up. So I'm going to speak this morning about recent results to measure the expansion rate of the universe. And this is something that has really exploded in our field in the last few decades, largely as a result of the launch of the Hubble Space Telescope in 1990 and the ability to measure how far away galaxies are. And that is a subject that began with the discovery of Edwin Hubble now about a century ago, allowing him to measure galaxies outside of our own Milky Way. And the explosion recently has come from new capability, new facilities, beginning with the Hubble Space Telescope, but also with our telescopes on Earth and new detectors, electronic detectors, that allow us to make much more precise measurements than were possible, for example, by Edwin Hubble. And we also have the ability to measure nearby stars very, very accurately using geometry And that has really improved in recent years because of a European satellite called Gaia, shown here. And we've had the opportunity to estimate how fast galaxies are moving, how fast the universe is expanding, using measurements of the radiation left over from the Big Bang. And the most recent measurements have come from a European satellite also by the name of Planck. And most exciting now on the horizon are observations that will be forthcoming from the James Webb Space Telescope, which was launched in December on Christmas Day of last year. And I will touch on what we will be able to do with the James Webb toward the end of the talk. So let me now say a few words about the general situation in cosmology, how we've come to the picture of the universe that we have today, why it has been so successful, and yet we now are appreciating that there may be cracks in what we refer to as our standard model. There are still some things yet to be discovered, and one of the new results that has emerged is a discrepancy, a tension, as people are referring to it, the measurement of how fast the universe is expanding today, a quantity we call the Hubble constant. There are different values that are being obtained in the classical way that we measure distances or the expansion rate, and what we're inferring from measurements of the leftover radiation from the Big Bang. But let me step back and describe to you how we came to the picture that we have today and what we're learning, and possibly the new physics still to be revealed. So if I could have the next slide, please. Now, in the 20th century, the number of discoveries in cosmology really accelerated, literally, along with the universe. So first was the discovery now almost 100 years ago that the universe is expanding. We do not live in a static universe, which was the view that we had before Edwin Hubble. And the universe is much larger than we had imagined before Hubble's discoveries. And the ability to make more and more accurate measurements of how fast the universe has expanded has really improved over the last few decades with the technology that I've just described. We also learned in the last century that the universe is composed of a substance we refer to as dark matter. That is, most of the mass in the universe is in a form that does not emit light. And we only infer its presence by the effect that the rest of the dark matter has on luminous matter, like stars or galaxies. And in fact, most of the matter in the universe turns out to be in this dark form. And I'll show you some of the evidence for that, why we think most of the matter in the universe is in this dark form. And in toward the end of the last century, the millennium, we made the discovery that not only is the universe expanding, as Edwin Hubble showed us, but it's also speeding up in its expansion. The universe is accelerating, and it is indicating that there is a type of perhaps energy we refer to as dark energy that is causing the universe to speed up, and is most likely a result of a repulsive form of gravity that is allowed within Einstein's general theory of relativity, but we don't yet understand the nature of dark energy. So these are some of the mysteries that are before us in the subject of cosmology today. So if we can go to the next slide, please. The discovery of the expansion came with Edwin Hubble in 1923, one of the first objects that he observed. He was interested in objects that were at the time called nebulae. Nebula is just a Latin word meaning fuzzy. And these were objects that some of them had spiral-looking shapes. You can see the Andromeda galaxy down toward the lower right of this image. Andromeda is one of the nearest galaxies to our own Milky Way galaxy. But at the time, when Hubble first began his observations, there was a debate about the nature of these nebulae. The question was, are these regions perhaps in our own Milky Way galaxy where gas and dust is forming new stars, stars that were collapsing out of this gas and dust that would be nearby? Or alternatively, could they be other, now we refer to galaxies in their own right, well outside the confines of the Milky Way? And Edwin Hubble was able to show by measuring stars within the Andromeda galaxy and other nearby galaxies that in fact these nebulae were like island universes, as they were referred to at the time, in their own right. That is, the Milky Way, our Milky Way galaxy, is not the extent of the entire universe, which was the prevailing view at that time. And Hubble in 1929 went on to show that not only are there other galaxies, but because he was able to measure their distances for the first time, and to make the discovery that the farther away a galaxy is, the faster that it appears to be moving away from us. The universe is undergoing an overall expansion. And that fit in at the time with the theoretical work of Albert Einstein, who developed the general theory of relativity in 1915. And what Einstein was able to show was that Einstein's theory was a theory of gravity. And the implication of the theory was that the universe had to either be expanding or contracting. It couldn't simply be stable, because gravity would pull objects together, or there was some outward expansion, but it couldn't be stable. It had to be in motion. And Einstein, at the time, there was no evidence in 1915 that the universe was expanding. That came in 1929 with Hubble's observations. And so he introduced into the general theory of relativity a term that forced the universe not to move, that forced the universe to be static, as a quantity we now refer to as the cosmological constant. And when Edwin Hubble discovered the expansion, Einstein is reported to have said that this was the biggest blunder in his life. But as we'll see, the discovery of the acceleration of the universe now actually suggests that Einstein was right after all, that there is a cosmological constant, and this is what's causing the universe to speed up in its expansion. Now, there were several decades where the measurement of the expansion rate of the universe turned out to be very, very challenging. Hubble's observations indicated initially a universe that was younger than its oldest stars, which of course is impossible. And it was the launch of the Hubble Space Telescope, shown here in the middle of this slide, that allowed us to make more accurate measurements of the expansion rate. This is what was called the key project of the Hubble Space Telescope, which was a project that I led in the 1990s, early 2000s. And for the first time, we were able to get above the Earth's atmosphere and to make much more accurate observations of the expansion rate. So if we could go to the next slide. This is the original diagram that Hubble plotted. It's a plot of velocity versus the distance to a galaxy. A very simple observation, which says what I said in words before, that the velocity of a galaxy is proportional to the distance from us. The farther away a galaxy is, the faster it appears to be moving away from us. There are a handful of galaxies at close distances, small velocities, that are moving toward us, and Andromeda is actually one of those. We and Andromeda will eventually collide in the very far future. But almost all galaxies that we observe, other than this handful of local galaxies, is participating in this overall expansion of space. If we could go to the next slide. So this is a version, a simplified version, and sorry to those of you who don't look at equations on a daily basis, but let me describe this in words. This is a an equation derived from Einstein's general theory of relativity, which describes the expansion of the universe. So on the left-hand side, this quantity h, which we refer to as the Hubble constant, the expansion today is the Hubble constant. It's actually a parameter that does evolve with time. We measure it locally. That's what we're doing with the Hubble Space Telescope, and we refer to that quantity as the Hubble constant. The Hubble constant gives us a measure of both the age and the size of the universe. And on the right hand side of the equation, beyond the second equal sign, we have terms that represent the amount of matter in the universe and this cosmological constant of Albert Einstein's, and also the geometry of the universe. And so the Hubble constant depends on how much matter there is in the universe and also this cosmological constant. And the way that we make now observations with the Hubble Space Telescope and also experiments on the ground to measure the matter density and so on, we can determine the ultimate evolution, the past evolution of the universe. And so our ability to make these measurements has improved over time. And now with the modern measurements, we're able to get to a few percent accuracy, whereas the value that Hubble measured in 1929, he was off by a factor of 7, simply because of the techniques that he had available to him at the time. He couldn't make more accurate measurements. So if you could go to the next slide. The measurements that Edwin Hubble made, what allowed him to determine the distances to galaxies, they were based on a type of star called a Cepheid variable. And it's a technique that we still use to this day. It's what we used for the key project with Hubble. And we will be using these same stars with the James Webb Space Telescope. These are stars that are more massive than our own sun. They're relatively young stars, and they're going through a phase in their overall evolution where the outer layers of the star, the atmosphere of the star, is moving in and out. It's pulsating. And in 1908, Henrietta Leavitt, shown in this slide, who was working at the Harvard College Observatory, made the discovery that the rate at which these stars change in their brightness or luminosity is directly proportional to how bright the star is. So there's a relationship between the period, the rate of motion of the atmosphere, and brightness. It's what we call the period luminosity relation, and today we refer to that as the Leavitt law, in analogy with what we refer to as the Hubble law, the relationship between velocity and distance to a galaxy. The implication of Henrietta Leavitt's discovery is that if we can measure the periods of the stars, the Cepheids that we see in other galaxies, and measure how bright they appear to us, then if we can measure these Cepheid variables in our own Milky Way galaxy locally, where we can use geometry to establish how bright, what the distance is, and therefore how intrinsically bright a Cepheid is for a given period. Then we can use what's called the inverse square law of light. We measure Cepheids in another galaxy, we compare them to those we can measure in the Milky Way, and then simply using the fact that light falls off as distance squared, we can compute the distance. So it's an enormously powerful technique for determining how far away a galaxy is. And the implications of this discovery, before the measurements and the discovery of Henrietta Leavitt, we didn't know how far away objects were from us. So if you look up at the night sky, you can see stars in 2 dimensions over the sky, but you don't know that third dimension, the distance. How far away is the object? And is the object bright because it's nearby? Or is it really intrinsically bright, could be far away, but we have no way of gauging that unless we know how far away the object is. And Henrietta Leavitt's observations provided the first means to allow the measurement of distances to galaxies. And that's the technique that Edwin Hubble used. It's what we used for our own key project with the Hubble Space Telescope. And as shown on the lower right is the Spitzer Space Telescope that operated at mid-infrared wavelengths, beyond the visible spectrum, and where, in fact, the James Webb Space Telescope also can operate. And so we used the Hubble to find Cepheids in nearby galaxies and to improve measurements of the distances to galaxies and the Hubble constant, the rate at which the universe is expanding. So if you could go to the next slide, please. Here is an example of a Leavitt law. This is one that we measured using the Spitzer Space Telescope. And what it's showing is the brightness, which increases upwards on the y-axis, the vertical axis, as a function of the period of the star, the rate at which the outer atmosphere is pulsating in and out over time. And you can see this very, very well-constrained tight correlation. And this is something that was not possible before we could get above the Earth's atmosphere and make these kinds of measurements. And the advantage of going to the infrared beyond the optical spectrum is that infrared wavelengths, infrared light can move past the dust particles that are formed in the atmospheres of stars. These dust particles then can obscure the light that's coming to us from these young Cepheid stars. And so we need to move to beyond the optical wavelength range to measure these distances to high accuracy. And that's something that just was not available, for example, to Edwin Hubble. So if we could go to the next slide. What we're doing is making measurements, as I mentioned, nearby. And we use geometry in the nearby universe. I'll say a little bit more about that in a moment. And then we step out into the realm where we can make measurements with the Hubble Space Telescope and soon to be with the James Webb Space Telescope. And we can measure distances to galaxies using Cepheids. And another technique, which we've developed in the last couple of decades, using a different kind of star than the Cepheid. These are lower mass stars than the sun, or comparable or lower, unlike the Cepheids that are very, very massive. And they also have the ability to provide information about the distances that rivals that of the Cepheids. So that provides for a very interesting and important check on the measurements that we're making with Cepheids. Now, these stars, the Cepheids and the red giants, are not bright enough to observe well out into the expansion. And we need to go out farther to make the most accurate measurements of the overall expansion rate. And so we use objects called supernovae, a particular type of supernova, type 1 supernova. Astronomers don't have very creative names sometimes. It's a type 1A supernova. And we can make measurements of those objects. They're extremely bright explosions of stars at the end of their lifetimes. We can make those measurements almost out to half or more the extent of the visible universe. And so we move out to the distant realm of the universe. And then we now can compare this oval, this ellipse here shape is an image of the background radiation, the remnant radiation from the Big Bang. And the different colors here indicate small differences in temperature, fluctuations in the temperature of the radiation coming from the Big Bang that are indicating different densities of material in the early universe. And the fluctuations in the temperature encode information about the expansion rate, the Hubble constant, the amount of dark matter, the amount of dark energy, and the composition of the universe. And so we have an end-to-end check, as it were. We can measure the expansion rate in the way I've been describing, using Cepheids and tip of the red giant branch and supernovae. We do that locally in our local volume, and then we can compare it with what we infer with the background radiation that we measure about 380,000 years after the Big Bang. And duos agree. It's a way of testing our model. If they don't agree, it has the possibility that they're of telling us about fundamental physics that we couldn't address any other way. We wouldn't have any other way of knowing about. If they agree, it tells us that our standard model is working well. And what I'll say is, to an accuracy of 10%, which for cosmology, up until a couple decades ago, we didn't know how fast the universe was expanding to better than a factor of 2. Now these very different techniques are agreeing at the 10% level. And the question before us is this a real difference? Is it significant? Are there still uncertainties in the measurements that could be causing the difference? Or have we measured this accurately enough to be able to infer that there's still something we don't understand about the nature of the universe? So that's what we're trying to establish now, and as we make more and more accurate observations. So we go to the next slide. What we do is, as I mentioned, is there are 3 steps essentially now to measuring the distances to galaxies and the overall expansion rate. The first on the left is that we use geometry. One technique is parallax, and there we simply use high school geometry. And for example, we can observe a star nearby. We can observe as the Earth is going about its annual revolution about the sun. We can observe the star from different vantage points. And you can see the triangle shown here. And literally, we use what we'll use in high school geometry to infer the distance to nearby objects, like Cepheids, like the red giant branch stars. And then, having established the fundamental 0 point, the calibration of how bright a Cepheid will be, or how bright a typical red giant branch star will be, we then use observations of the Hubble Space Telescope, shown in the middle. That's the realm of measurements of Hubble out to distances of 30 megaparsecs or so. That's 100 million light years. And that's where we measure the Cepheids and these red giant branch stars. Red giant branch stars are shown in the circles here. And then we step out to the realm of the supernovae, which are even brighter, these explosions of stars at the ends of their lifetimes, and measure the Hubble constant in the distant universe. So those are the 3 steps. And then if we go to the next slide, I'm showing here on the left the original observations we saw earlier from Edwin Hubble, the velocity versus distance plot that established that the universe is expanding. And on the right is the final plot from our Hubble Key project. And the data that Edwin Hubble had available to him fit into the first tick mark of the plot that I'm showing here on the right. And what we did with the Hubble Space Telescope was to measure again the expansion rate, velocity versus distance, and we did it in 5 different ways that allowed us to combine the results in the end and get a very overall robust measurement of the uncertainty in the measurement. So we're able to measure the Hubble constant to a level of 10%. Before that, we had a factor of 2 uncertainty that remained, that could not have been solved. Slight technical glitch there. Okay, next slide, please. Now, I mentioned that most of the matter in the universe we have discovered is in this dark form, not luminous matter. This is now, these are observations that have been made in many, many different ways by studying the motions of stars within galaxies, and also the motions of galaxies within clusters of galaxies and measurements of hot X-ray gas in galaxies and clusters of galaxies. I'm not going to go into detail here. The point that I want to make is simply that different ways of looking at the problem have all pointed us in the same direction. Most of the matter in the universe is in this dark form. There's about 6 times more dark matter than luminous matter. And this is an observation that was first made in the 1930s. And so almost 100 years now of independent measurements of the amount of dark matter have led to this very consistent story. The difficulty is we don't yet know what the dark matter is. If you go to the next slide, please. The nature of the dark matter at the moment, the best explanation that cosmologists have left standing. Many alternatives have been put forward over the last few decades, but the most plausible explanation appears to be a particle that is left over from the Big Bang. It's a particle that interacts gravitationally with ordinary matter, but perhaps only weakly with luminous matter. And so this is something that there are experiments around the world that have set out to try and detect the nature, the interaction of dark matter with luminous matter. But so far, there has not been an experimental discovery of the dark matter particle, but a number of experiments around the world are actively trying to find the dark matter particle. If we go to the next slide, I think the video won't work here, but this was a station that shows the effect of dark matter in the development of the large-scale structure in the universe, and we are not able to explain the distribution of galaxies or clusters of galaxies on the sky without having a dark matter. And so computer simulations now with literally billions of particles that simulate the dark matter can reproduce very accurately the distribution of galaxies on the sky that we see, and in a way that is not possible without the existence of dark matter. So if we go to the next slide. Next, yeah, thanks. The other part of the cosmic pie chart, as it were, is the dark energy component of the universe, which turns out to be about 70%, about 2/3 of the overall mass plus energy density in the universe is in this dark energy form that's causing the universe to speed up. And so we go to the next slide that shows this cosmic pie chart. And, getting ahead of myself, the evidence for this dark energy came first from the study of these type 1a supernovae that I mentioned early that we use to determine the Hubble constant, also measurements of these supernovae at very large distances. So if we go to the next slide, this is now a Hubble diagram that extends much farther than when we measure the Hubble expansion locally. But there are now thousands of supernovae that have been measured and that provide evidence for the acceleration of the universe. So that has come from the type 1a supernovae, but also from measurements of the microwave background, the cosmic background radiation, as well as measurements of the matter in the universe. So if we go to the next slide, I'm going to just quickly summarize what the information on this slide, which just tells us that the equations from general relativity, again, so this is a second equation in addition to the one that I showed you earlier, that allows for a repulsive form of gravity. And that is what Albert Einstein's theory allows, not allowable in Newton's theory of gravity. but the overall message is that you could have a substance with a ratio of its pressure to its density that is negative, and that is what causes the universe to speed up. So I just want to make the point that this is consistent with the equations from general relativity. We don't yet understand the nature of this dark energy, but it is consistent with general relativity. Okay, let's go on to the next slide. And I'm going to skip this one now and continue. Here is the cosmic pie chart, which just makes the point that 70% of the overall composition of the universe now is in this form of dark energy. About 1/3 of the composition of the universe is in matter, and most of the matter in this dark form. The luminous matter, the stars, planets, us, is only about 1% of the overall composition of the universe. We are really literally the tip of the iceberg. And these are new discoveries in the last couple of decades, the existence of this dark energy, the dark matter. As I said, the evidence has been accumulating over recent decades. But there are now many ways to make these measurements independently. And this, what we refer to as the standard, this symbol here, the upside down V, is a cosmological constant from Albert Einstein, represents the cosmological constant, and CDM stands for cold dark matter, this dark matter component that I've been describing. So this model does extremely well at describing the universe that we observe with our telescopes. And if you go to the next slide, what's kind of remarkable is that this model is very predictive. It goes from measurements of the cosmic microwave background, shown again in this ellipse here, these fluctuations in the temperature. And if we allow for dark matter and the early fluctuations to grow by gravity, matter is an attractive force, and the structures that we see today in the universe, the distribution of galaxies on the largest scale, are extremely well fit by this standard model. The standard model that has about 1/3 matter, 2/3 dark energy, and most of the matter is in a dark form. Now the question becomes, we don't yet, as I've described, understand what the dark matter particle is. What is the dark matter? We have lots of evidence that it exists, but we haven't yet been able to ascertain what it is. And the dark energy is very consistent with the general theory of relativity established by Albert Einstein, but we don't know, again, what is causing the universe to accelerate. What exactly is the dark energy? How does it evolve with time, if it does at all? And if we go to the next slide, that's what we're now trying to understand. Could there be something missing from this standard model? How do we test that? Well, we can make measurements locally for what the expansion rate is today. We have this standard model that is predictive. Given a certain amount of dark matter and dark energy, it tells us what the expansion rate will be today. We let these fluctuations in the Big Bang temperature density evolve them forward, and we can compare what does it say about the expansion rate today. It's very predictive. Do they agree? And we go to the next slide. And that's what has been described recently as tension in measurements of the Hubble constant. If we measure the Hubble constant based on the cosmic microwave background, we infer it from this model, and so we get a value of the Hubble constant of 67. And if we measure it using Cepheids later in the universe, as an evolutionary image here, going from the Big Bang through the microwave background observations to the galaxies we observe today. And when we make our measurements with Cepheids, and I'll talk about the tip of the red giant branch in a moment, we get a higher value of the expansion rate. And again, is this a significant difference? We don't yet know. That's what we're trying to end. I'm not currently seeing the slide, so I will wait for that to come up. Yeah, next slide. These are measurements now coming from the microwave background. So again, this ellipse showing the difference in temperature. The two arrows there represent two different temperatures. We can measure those different temperatures across the sky, and the fluctuations in those temperatures are indicated, represented here on the graph. You see these fluctuations, these bumps in what's called the power spectrum of these fluctuations. And what's really intriguing about this particular plot is that there's a line that is drawn showing these fluctuations. That line is the prediction of the standard cosmological model, this lambda cold dark matter model that I've been describing. It's a fit to the fluctuations in the temperature, and it is a remarkable fit. And these temperature fluctuations now have been measured to 1/1000th% accuracy. This is astounding level of accuracy for cosmology. We would not have been able to use those words in the same sentence a few decades ago, accuracy and cosmology. It represents a huge leap forward. And as I've mentioned, if we use these data from the microwave background and then infer based on this fit to this cosmological model, this predictive cosmological model, we get a lower value of the Hubble constant than we do when we use this classical measurement using the Cepheid variables. So if I could go to the next slide. And I have been describing a little what the Hubble Space Telescope has done for us, but essentially allowing us to get above the Earth's atmosphere, which is turbulent, which causes blurring of images, these Cepheid stars as we're observing them through the atmosphere. The clarity that we can get, the higher resolution, is if we're putting on eyeglasses and improving our resolution, has been enormous. That's what has allowed us to make these leaps forward. So we go to the next slide. I'm showing here the value of the Hubble constant that we have been getting as a function of time of the measurement. And on the left is our value that we published in 2001, our Hubble Key project. And the uncertainty looks large relative to what we've done recently, but that's the 10% uncertainty that improved over the factor of 2 that's way off scale of this plot that existed before we could use Hubble. And you can see that the value of the Hubble constant that is being plotted as a function of time has stayed pretty constant at this in the low 70s. But what has decreased with time are the sizes of the uncertainty. The error bars shown here, the vertical bars, have shrunk with time. The measurements have gotten more and more accurate. If we go to the next slide, I'm showing measurements of the Hubble constant that come from the interpretation of the fluctuations in the cosmic microwave background temperature. And those have come down with time as the measurements have gotten more and more accurate. And the very tiny error bars are the measurements that are coming from the Planck satellite that I mentioned in the introduction to my talk. So those measurements have vastly improved. And the next slide shows a new technique that I think is going to be very promising in the future using measurements of gravitational waves. And there's only one object so far that's been measured using this technique, and you can see the uncertainties are large, but it holds great promise for the future. So if we go to the next slide, that now shows the classical Cepheid route compared with the measurements in black from the cosmic microwave background. And you can see that the value of the Hubble constant disagrees, and the uncertainties, the error bars that are shown, don't even overlap. So this is what has been referred to as the tension that we're seeing. And the question is, how significant is this difference? So our group decided, after making all the measurements with Cepheids with the Hubble Key Project, and understanding that any one method is going to have uncertainties that are inherent to the technique itself. And the only way that we will be able to determine if there are what we refer to as a systematic uncertainty, that is, you can make the measurement as many, many times as you want, but if there's something inherent in the technique that is an uncertainty, no matter how many times you make the measurement, you're going to get the same systematic uncertainty. And the only way you can assess the size of the systematic uncertainty is to do the measurement in a completely independent way. So that's why we have been investing a lot of time now into a different technique, these red giant branch stars. So let me go to the next slide. And this is a slide that it shows some of the possibilities if the discrepancy is real. How would you explain it? And what I'll say to this slide is that there are now about 1,000 papers that have looked at this question of the difference in the Hubble constant locally and compared to the microwave background. And no one yet has come up with a solution, a physical reason for understanding why the Hubble constant would be different, what could be missing from the standard model. If you change something somewhere, it has an effect somewhere else and doesn't agree with observations elsewhere. And so if the discrepancy is real, which would be very exciting, it would indicate new physics, something like this. But of the examples that I've shown here, none of them yet has been able to plausibly explain why the Hubble constant nearby would be so different than locally. So that remains to be determined if it's real. So let's move on to the next slide. And let me say a little bit about these red giant branch stars that we're now using to measure distances in the same distance range, that second tier of the distance ladder, the same distance range as the Cepheids. So these are low mass stars, and when they reach a certain luminosity, they rearrange the internal structure of the star, and the overall effect is that they reach a constant luminosity during their evolution, and then they disappear. And so we go out and we measure thousands of these red giant branch stars in the outer regions of a galaxy, away from the gas and dust that the Cepheids are contained in. So the Cepheids are young stars, and they're in the disks where new stars are forming. These red giant branch stars have an advantage that we can get away from all the gas and the dust, and they're very isolated. They're not close together the way the stars in the disk are. So we can make very, very accurate measurements of their brightness. So if we go to the next slide, these are some of the fields that we've used with the Hubble Space Telescope, and the squares here show the locations of the camera where we pointed the camera with Hubble away from the disk. You can see the pretty spiral galaxies or other kinds of galaxy, and we're trying to get away from most of the light of the galaxy so that we can make more accurate observations. So go to the next slide. It's just showing an example here of one of our target galaxies, and you can see the red outline of the camera where it was pointed in this galaxy. And lower right, you can see circles around individual stars, and the Cepheids I'm not showing you right now, but they are on top of other stars in the disk. It's very hard to separate the light of a Cepheid from its neighbors, but very easy for these tip of the red giant branch stars. So that's a really nice advantage in making those kinds of measurements. We could go to the next slide, please. I just want to say a word about, as I mentioned, we have to step out into the universe at larger distances than we can measure with tip of the red giant branch or Cepheids. So we use supernovae And we used the telescopes at Las Campanas in Chile to do that, the Carnegie Supernova Project. If we go to the next slide, we had a 10-year project to measure these supernovae and to measure the Hubble diagram velocity versus distance out into the farther realm of the universe where the Hubble constant can be measured. So we go to the next slide. This just shows another version of the velocity versus distance plot, and the red points are coming from the nearby stars, red giants, and the blue points are the measurements of the type 1a supernovae that allow us to make the Hubble constant measurements farther out. If we go to the next slide, this is now again a version of the plot. The Hubble constant is a function of time. The blue are the Cepheids. The black, again, are the microwave background observations. And the red now are what we're finding from the tip of the red giant branch. So we had expected, I think, to find that we would either agree with the Cepheids or with the cosmic microwave background, and we would resolve this discrepancy. But where we landed was right in the middle. It's just where we landed. And you can see that the error bars are close in both cases, close to both the microwave background in the black and also the Cepheids. And so the difference here, this is not telling us about fundamental new physics in the early universe. It's telling us that there's something that's different in the measurements of the tip of the red giant branch and the Cepheids. And that's something that we will need to understand before we can claim that there's something missing from the standard model. This is an issue of distances, and it's likely an issue of understanding where the systematic uncertainties reside. Is it in the Cepheids? Is it in the tip of the red giant branch, or some combination of the two? And that's where James Webb is going to enter and allow us to address that question of the systematics. So if we could go to the next slide. This is a comparison of the distances between the Cepheids and the tip of the red giant branch technique. And I just show in the red here that these are the data that we're getting from Hubble. So these are more distant than the points in black, where the agreement is very good in the nearby galaxies. But as we go out into the realm of the Hubble Space Telescope, farther galaxies where the distances are harder to measure, there's the difference. And this is the difference that we now need to understand. We don't know how this is going to resolve in the end. So if we go to the next slide. We've spent the last couple of years trying to test and improve the constraints that are coming from the tip of the red giant branch method using a number of different measurements. And so I'm showing here a galaxy that is one of the calibrating galaxies for both Cepheids and the tip of the red giant branch. And we've made very extensive measurements in the halo of this galaxy. And we find excellent agreement with the results that I showed you before that are in the middle between the microwave background and the Cepheids. If we could go to the next slide. We've also looked at red giant branch stars in our own Milky Way galaxy, and these are stars for which we can measure geometric parallaxes. So it's another test of the calibration, the measurements of the tip of the red giant branch. It also is agreeing at a 1% level with our earlier measurements that I showed you. And if we can advance to the next slide, these are measurements in our nearby neighbors, the Large Magellanic Cloud and the Small Magellanic Cloud, where we can make very precise measurements of the brightness at the tips of the horizontal line here, which shows you the dividing line where these stars change in their luminosity during their evolution. And the very narrow peak to the right, you can make this measurement extremely accurately. And again, we're measuring these stars with Hubble out in the halos of galaxies where we can make measurements very, very accurately. So if we go to the next slide, this is a comparison of the different techniques now for measuring the Hubble constant. And so to the left, the black curve shows the Hubble constant that you get, about 67, coming from the Planck measurements of the microwave background. The blue shows the Cepheids on the right, and the uncertainties, the width of these parabolae here show the uncertainties that have been published by each of the groups. So the Cepheid measurement to the right, here's our tip of the red giant branch in the red. And the other measurements that are shown here, these are other techniques where you can see that the uncertainties are much larger still than coming from the tip of the red giant branch or the Cepheids. So there is this significant difference between the two, which we have not yet resolved. And if we go to the next slide, that's where I'm most excited now with coming observations that we will get from the James Webb Space Telescope. So this telescope, as you probably know, was launched this past Christmas Day, December, and had a few-month trajectory to get 1 million miles away from the Earth, where it is now in orbit, trailing the Earth around the sun. And the launch was so successful that very little fuel was required. So to get to the trajectory, to park it in its place where it will now reside and undertake its observations, left enough fuel over that the lifetime of this telescope is likely to be in excess of 20 years. And so they planned to have 5, maybe 10, and now that's doubled. So it's just extraordinarily exciting for us in the astronomical community. If you can go to the next slide. You may have seen, I hope you've seen, and if you haven't, I encourage you to go on the web and look at the new images that are coming out of the James Webb Space Telescope. They are spectacular. One of the really exciting aspects of all of this is that the engineers who planned this telescope were, of course, had to be conservative in their estimates, the tolerances that they could have in the various components. And everything has worked so well that it's actually operating at much better than expected level. It's the resolution is a factor of 2 better than they had predicted at the wavelengths that we're going to be using in studying these red giant branch and Cepheids. And you can see also in the lower middle here, a recent beautiful image of Jupiter in our own solar system. To the bottom right there is a deep field taken moderately short exposure. A similar exposure that was taken with Hubble was taken over literally days, weeks long integration. So when this telescope starts integrating and going very deep, I think we just can't even really imagine what it's going to uncover. It's very, very exciting. The top right, this is a quintet of galaxies. One of them to the left there is actually nearby. It's similar to the ones that we're going to be observing for Cepheids and tip of the red giant branch. So we've been analyzing those data and trying to understand how best to analyze these new kinds of data coming from James Webb. So our group, we applied for time on James Webb. We will start observing in the first cycle, open to the community, and we'll start observing in November of this year through October of next year, about 1 galaxy per month. And our goal is to observe Cepheids and red giant branch stars, and a third type of star that we've been studying and calibrating to measure distances. So the strength of this telescope, if we can go to the next slide, that James Webb operates at near infrared and mid-infrared wavelengths, and it can peer through dust. So as I was telling you, the dust in the young regions where Cepheids are forming, we can, if we observe in the optical, this is the Eagle Nebula on the left, and you can see these dark patches. They're actually stars embedded in these regions where new stars are forming in our own Milky Way. If you go to the next slide, this shows a near-infrared image. What James Webb will see, and so you can begin to see that there are stars shining through the dark part because the long wavelengths can get out. And the next slide shows the mid-infrared, which is the dust itself emitting. So the resolution of this telescope is about 3 times that we can get from Hubble. So we'll see if these Cepheids are crowded, we'll see how the reddening has affected them, and we can also look for other kinds of systematic effects. All of the galaxies we're measuring will do these different techniques in the same galaxies. So we'll be able to get to the bottom of why the Cepheids and tip of the red giant branch are different. And do they give a high value of the Hubble constant or a small value? So that's all coming. If you could go to the next slide. That the task before us again is to check all the rungs of this distance scale ladder, and that is really what James Webb now is perfectly designed to do for many, many reasons. So if we go to the next slide, and this is my final slide. What we're really excited about in the next few years is the ability now to get at what is causing this tension. And this up on the upper left, the Gaia satellite that's measuring nearby galaxies, it will come out with new results in the next couple of years. We're still using Hubble to improve our measurements of nearby galaxies using optical wavelengths, and now we have James Webb. And as I mentioned, our program is to observe the same galaxies with different techniques. These galaxies can only be at one distance. So it's not as if the discrepancy is telling us something about the early universe. It's telling us about astrophysics, potentially, or systematics, and that's what we will discover. So this high resolution, high sensitivity, the ability to look through dust will, I think, allow us to resolve this interesting tension, and I'm really excited to see what comes of it. And I will stop there, and I'm happy to answer any questions that you might have, and thanks for putting up with the technical challenges.
Well, many thanks. It was an excellent talk. And we do have several questions. Some of them are more related to the actual telescope, and some of them are more related to the actual physics and the findings that are coming from there. So we're going to start with the question about the new telescope, the Webb telescope. What can we learn from the Webb telescope that was not possible with the predecessor, the Hubble telescope?
Yeah, I think there are a lot of things that we're going to learn, and I think one of the things I would start off saying is that for me, what will be most exciting is what we can't even imagine right now. And what we have seen over literally centuries since Galilei first started observing with his telescope in 1610 is that every time we've had new capability, we have made new discoveries. And this telescope is, its diameter, the mirror is a 6.5 meter mirror compared to Hubble's, which is 2.5 meters. So it has about 10 times the sensitivity goes as the square of the diameter. So it will be able to see farther back, it will be able to see fainter objects, and it will have higher resolution, about 3 times higher resolution. So one of the main objectives of the telescope is to study galaxies in the early universe. And so that deep field that I showed you, we now are able with Hubble to measure galaxies back to about 1 billion years after the Big Bang. And the cosmic microwave background that I've been describing during the talk, that's a measure of the universe at about 380,000 years after the Big Bang. And so that region between 380,000 and 1 billion 1 billion years after the Big Bang is a region we refer to as the Dark Ages. We have no information about what happened at that time, except that we know galaxies formed, and we have lots of ideas of how that happened, but we'll witness that directly now. And because of its infrared sensitivity and because of the expansion of the universe, light from distant galaxies is shifted to the red. And so James Webb is optimized for the infrared, and we'll see these galaxies for the first time. So that is going to be really, really interesting. And another area I think that will be very exciting, and there are many, many, I don't have time to go into them all, but another one I think that really will open up new windows is the study of extrasolar planets. And because of the high resolution again and the infrared sensitivity, right now we can measure planets around other stars and measure their atmospheres and see the composition of the atmospheres. And the ability of the infrared now to measure, for example, things like carbon dioxide, the first measurement of carbon dioxide in an atmosphere around another planet was just announced a few days ago. And there will be a complementarity between the kinds of molecules that we'll measure from optical spectra and what you can measure from the infrared. And I think astronomers are getting closer and closer to the possibility of actually detecting life on a planet outside of the Earth, which is going to be a phenomenally exciting discovery when that comes. Now, what we know now is that on average, there is an Earth-mass planet, one for every star in the Milky Way. That's about 100 billion stars. We now have a candidate list of nearby planets that's come from a satellite called TESS. These are nearby stars that we can study. And again, as I said, every time you get new capability, in this case, resolution and sensitivity and wavelength coverage, we're going to learn something new. So if you hear astronomers talking about James Webb now and the excitement that we feel, it's we're on the threshold of really exciting new discoveries. And as I said, some of them we can't even anticipate. But pretty much every field in astronomy now, there are questions that we can't answer with Hubble just because of lack of sensitivity or wavelength coverage. And so pretty much every field is going to, I think, have something new come out of the James Webb Space Telescope observations. It's a very exciting time.
Thank you very much. What is the advantage of having telescopes outside orbiting our planet versus these series of arrays of multiple telescopes located in different regions of the planet? For example, those that were used to confirm the existence of gravitational waves. Can the findings and images from these two types of telescopes be integrated, or how do they differ, and what are, again, advantages and disadvantages for that?
Yes, these types of telescopes are very complementary, and we're studying different aspects, sometimes of a similar problem, coming at them from a different vantage point. So James Webb is, as I mentioned, 1 million miles from Earth. The Hubble Space Telescope is 340 miles up, I believe, about 600 kilometers, and it's Earth orbit. The James Webb, because it's detecting infrared radiation, which is like heat radiation, any sources of heat will be a source of noise for James Webb. So we had to get away from the Earth. And so it's out at this so-called Lagrange point, and it has this tremendous heat shield or sun shield that protects the telescope from sources of heat. The gravitational wave, well, let me say, first of all, also optical telescopes on the Earth. So we have telescopes that we use where we can make observations in the optical, but the infrared and the ultraviolet are primarily obscured. I mean, there are things in the atmosphere of the Earth that make those kinds of observations very, very difficult. And so getting into space, if you're going to observe in the infrared, you really want to be in space to make those observations. Then there's this whole new window of gravitational wave astronomy that's been opened up by experiments like LIGO. and they're measuring measurement fluctuations in space-time as you have massive objects, for example, binary black holes or binary neutron stars that are spiraling in toward each other and that are actually causing these fluctuations in space and time predicted by Albert Einstein. And so it is possible to make measurements, and I showed very quickly this one observation of a neutron star binary that allows you to estimate the Hubble constant. And it's a completely different technique, which I think is extremely important. As I mentioned, each of these techniques has uncertainties that may be systematic, that is, go in one direction or another, not simply random fluctuations. And so the more kinds of techniques that we have of high accuracy that we can measure the Hubble constant with, then the more in the end we will come out with a robust value that I think everybody will agree is has been measured to the accuracy, for example, in the microwave background. And that's at a level of better than 1%. So quite generally, I just want to add that, in the days of Hubble and optical telescopes, those are extremely complementary. You do different things with telescopes in space than you do on Earth. And the same is now true for James Webb and the next generation of telescopes that we're planning on the ground, these giant telescopes. There are 3 in the planning stages, 1 in Europe, 2 in the US. The planning for them, one, the European and our Giant Magellan Telescope, which is a telescope project that I led for 12 years. Those 2 telescopes, the European one and the Giant Magellan Telescope, will be in Chile, and then the 30-meter telescope, they're trying to decide what site they will use, but it will be in the northern hemisphere. So these very different telescopes will do very different kinds of things, but in the end, we're getting different information that allows us to answer the questions that we're posing. And in the end, for the various questions that we're asking, the question will be, how consistent are these? What are we learning? And as I said earlier on, I think the most exciting kinds of discoveries are those that we can't even imagine right now. We don't even know the questions to ask. And that will be fun.
Yeah, thank you very much. Michelle Franco, she asked, what does the images and the efforts on getting better telescopes has, what is the interaction with this space program, for example, the mission from NASA of Artemis? How are these images going to help us, if at all, in this space race to get humans back to the moon and to other planets like Mars?
I think probably they're separate. I think Artemis is going to allow us to learn again how to operate in space. We haven't been to the moon in 50 years, and a lot has changed in our capability and also our understanding of availability of water and our need to understand how much water is available on the moon and could we use it. Mars is a very challenging environment, and eventually there is, the possibility of human exploration of Mars, and that will come, but it's, I think, well into the future, and there's a lot that will need to be done by robots before it makes sense to send humans to Mars. Part of the challenge, of course, being just the environment in space, so the danger of radiation to astronauts in space and how to protect them. And so I think, we as a species are explorers. We explore the moon. We want to explore nearby planets, and we're doing that in many ways. And then we want to explore even more distant reaches of the universe, and that's where the telescopes come in. So I think, in a sense, they're complementary again, but quite distinct in that. And I think partly what's also changing is the ability now for it's not just NASA, not just governments internationally that are allowing space travel, space study, launches of satellites and communication satellites and so on. But individuals now and companies can do that. So there's competition, and I think new resources that will open up in future. So I think they're distinct, but part of the same human desire, curiosity to explore.
Thank you. Alfred is asking us, why is the universe expanding? In your talk, you give various lines of evidence for this expansion of the universe, and what he's asking is, why is this happening? Is there like a big attractor or multiple attractors that are sort of pulling galaxies towards them? What is the reason for this expansion?
Yeah, our current picture, and based on the evidence that Edwin Hubble first uncovered, we see galaxies today expanding, and that would imply that earlier in the universe, if the universe has been expanding, that galaxies would have been closer together. You go even farther back in time, they're closer. So that there would be a time when the universe would have been very dense. And that observation, combined with Albert Einstein's development of the general theory of relativity, led to the picture of what we now refer to as the Big Bang universe. So that the universe, so in this early stage, the universe would have been very dense, very hot, and gave rise to an early explosion of this idea of an early explosion, after which galaxy or matter has been expanding. And so if you ask what is the evidence for the Big Bang, there's first the expansion of the universe, but also you can calculate very precisely, if the temperature and density had been so high in the universe, what are the elements that would have formed? So you would end up with hydrogen, the light elements forming very early within the first few minutes of the Big Bang. And you can predict the density of hydrogen and helium and deuterium, lithium, and these light elements. And they have densities, predicted densities, that differ by 9 orders of magnitude. And you can actually measure those now, and those agree remarkably well with the predictions of the Big Bang. And then there's the existence of the Big Bang radiation. And so in every direction that we look, there is this cooled radiation at a temperature of about 3 degrees above absolute zero. And in every direction that we look. And so this is what you would predict from this hot Big Bang beginning. As the universe is expanding, it is cooling, and today we observe that remnant radiation at about 3 degrees Kelvin. And the fluctuations, these tiny measurements that are now being made at an accuracy of about 1/1000%, it's really quite remarkable, the kind of accuracy now that is possible to test the Big Bang. So the universe began in this hot, dense phase, and has been expanding ever since. Well, let me stop there, because I think that answers, I hope that answers the question that was asked.
Yeah, I think so too. Thank you very much. Well, we're nearing the end of this session, so I'm going to put forward the last question. Thanks to everybody who has been sending comments and questions. Unfortunately, always time is a limiting factor. The last question is, are Cepheids distributed uniformly across the universe, or are they found in clusters?
Cepheids are found in galaxies that are still forming stars today. So we distinguish different types of galaxies. I don't know if I've just been cut off. I'll continue in case not. There are spiral galaxies and elliptical galaxies, and also more irregular galaxies. But we use Cepheids in spiral galaxies, and we find them in the arms of these spirals where new star formation is occurring. And so they're clumped in the sense of we only find them in galaxies, and we only find them in
Creo que tuvimos un problema técnico con el sonido.
Now I see you again. I don't know if that got through.
No, I think we lost the last 30 seconds or so.
Okay. So I was describing that we see different kinds of galaxies. There are spiral galaxies and elliptical galaxies and also irregular shaped galaxies. We find Cepheids in spiral galaxies, along the spiral arms generally in these galaxies, regions where new stars are forming out of gas and dust. And so we don't find them in elliptical galaxies, and these are older galaxies without new star formation. So they're not distributed generally across the universe. They're within galaxies and confined also primarily to spiral arms, which are the places where new star formation is occurring.
Thank you very much. Well, I think we all agree that this was a fantastic presentation by Dr. Freedman. We're particularly grateful to her because she agreed to give her talk despite major blackouts in the Wi-Fi signal at the University of Chicago today. So thank you very much for persevering with this and delivering a fantastic presentation.
I'll just add, I'm proud at the moment, so it's not the University of Chicago. But yes, thank you for your patience with the technical difficulties.
No problem at all. I think it was well worth the wait for everybody. Muchas gracias a todos los que nos están acompañando el día de hoy. Como ya dijimos, hubo algunos problemas técnicos al principio de la presentación, completamente fuera de nuestro control. Y bueno, agradecemos como siempre su presencia y en este caso también su paciencia. Creo que todos estamos de acuerdo en que fue una fantástica presentación que nos da una ventana a lo que la nueva tecnología nos permite en términos de entender mejor el universo que nos rodea. Vamos bueno, en nombre de todas las instituciones que forman parte del Consorcio de Universidades por la Ciencia, a título personal les agradezco que nos hayan acompañado y ahora vamos a escuchar unas palabras del doctor Jaime Urrutia, quien es miembro del Consejo de Fundación UNAM y también miembro del Colegio Nacional, y posteriormente cerrará la sesión el licenciado Dionisio Meade, quien es presidente de Fundación UNAM. Muchas gracias.
Thanks very much, and just to congratulate Professor Freedman for her studies and this conference. Thanks to all for accompanying us, and this has been a really interesting presentation. The new capabilities provided by first by the Hubble telescope and now by the Webb Space Telescope are amazing, and the results are still to come, and we look forward to continue in contact with Professor Freedman to learn more about the studies. On behalf of the Fundación UNAM, we thank UNAM Chicago Center for coordinating this wonderful presentation. Thanks Erika, Evelyn, Alberto Fonserrada, Guillermo Pulido, and we look forward for continuing this collaboration. And the international collaboration is one of the priorities of Fundación UNAM. And the aim of this new consortium of universities for science is to provide the means to keep everybody in contact. Thanks very much, and thanks, Dr. Freedman. And we now pass to our president of the UNAM Foundation, Dionisio, Meade, for the final remarks. Thanks to all. Thanks, Araxi, for conducting the discussion and for organizing this consortium for universities of science.
Pues muchas gracias a todos, muchas gracias a Wendy por esta presentación formidable. Y la verdad, habíamos estado con la ilusión de poder ver y comparar pues lo muy valioso que ya nos había parecido las vistas que teníamos a través del telescopio Hubble, y ahora quedamos pasmados con las que nos ofrece el telescopio James Webb. Ese es un universo que nos abre horizontes de investigación verdaderamente infinitos, y la capacidad de la ciencia pues tiene al mismo tiempo la de abrir espacios de investigación que no nos habíamos imaginado. Y yo creo que lo que hoy vemos, que lo que hoy podemos hacer, lo que hoy se nos ofrece como horizonte para que muchos jóvenes puedan hacer de la astronomía una opción en su vida personal y profesional, pues se vuelve una realidad, yo diría prácticamente impostergable. Para quienes son un poco más de mayor edad, como es mi caso, apenas si soñábamos con películas de ficción cuando se generaba un viaje a la luna, pero no imaginábamos que el día de mañana se iba a poder materializar con una realidad, y que pues unos telescopios como los que se han puesto ya en el espacio nos iban a abrir un universo tan grande, tan formidable como el que hoy conocemos. Esperábamos con ilusión ayer que pudiera salir el cohete con el proyecto Artemisa, pero lo seguimos teniendo con ilusión porque cada uno de ellos nos ofrece nuevas visiones, nuevas ilusiones, nuevas esperanzas y nuevos campos para la investigación científica. A nosotros en Fundación UNAM, en este proyecto que vamos de la mano con Araxi en el Consorcio, con Jaime en el Colegio Nacional, nos ilusiona mucho que podamos presentar estas opciones de investigación, porque creemos que justamente ahí se encuentra el semillero del futuro. Ahí se encuentran las posibilidades de que muchos jóvenes encuentren un horizonte de realización, un horizonte de entrega, un horizonte de apasionamiento por la investigación científica. En una ocasión que contábamos aquí con la presencia de un premio Nobel, le preguntamos que cuál era el secreto que le había llevado a esa altísima distinción, y él nos dijo la curiosidad científica. Y yo creo que si algo puede suscitar curiosidad científica es una presentación como la que Wendy nos ha hecho el día de hoy. Muchísimas gracias por eso. Muchas gracias a Araxi por esta idea del consorcio que nos ha vinculado a tantos alrededor de un proyecto, de una investigación, de un intercambio de información y de conocimiento, y a Jaime Urrutia, que ha puesto todo su entusiasmo y todo su instrumental para que podamos ir juntos en este proyecto. Gracias a Elderly, gracias también por todos quienes nos apoyaron para hacer esta presentación, y pues seguimos comunicados. Habrá cada martes una presentación alrededor de estos temas de investigaciones en curso. El de hoy ha sido una muestra y un ejemplo, y esto se hermana muy bien con lo que hemos venido haciendo en nuestros documentales por la ciencia, en donde precisamente estamos presentando el que será ya probablemente el último capítulo de esta serie, de esta investigación, de estos despegue, una segunda edición con todas estas presentaciones que seguramente será mucho más rica, más nutritiva y más apetitosa para quienes han hecho de su vida la investigación científica. Gracias a todos y muy buenas tardes.
Muchas gracias, Dionisio, por estas palabras. Como ya se mencionó, pues esta es una conferencia en colaboración con la representación de la UNAM en Chicago. Entonces, no sé si Alberto o Erika quisieran decir algunas palabras.
Adelante, Alberto.
¿Los dos?
Bueno, yo nada más agradecer a la Fundación a nombre del doctor Guillermo Pulido y de todo el equipo de UNAM Chicago por la organización de estas magníficas mesas. And I want to thank Wendy, Freedman, and all the team in the University of Chicago. We're very proud of this partnership we're developing, which keeps growing and growing. And we're excited about the new projects that we're going to engage on. Stay tuned for September, because we have another one at the end of September where we're going to be involved. And I just want to thank everybody for tuning in.
Erika?
Just thanks again to Wendy Freedman and to all the team at University of Chicago for collaborating with UNAM Chicago and Fundación UNAM. Thank you very much.
Muchas gracias. Bueno, ahora sí, cerramos y nos despedimos. Hasta la próxima. Pues esperamos el siguiente martes.
Recording stopped.
Okay.
Muchas gracias de nuevo. Thank you very much, Wendy. Thank you, Alberto. Thank you, Elderly. Thank you, Araxi and Jaime. It was a very, very good presentation.
Where are you